That's our first seminar. It's about work and energy theorems and the principle of virtual work, just to recall and prepare basic knowledge of mechanics. The principle of virtual work just comes in two variants: the principle of virtual displacements, the basis of finite element method, and to determine the generalized force values, and the principle of virtual forces, just to determine the generalized displacement values and the basis of traditional manual calculations. I'm sure that you have learned about that in your basis education. Nevertheless, for the rest of this workshop, it's enough to concentrate on the principle of virtual displacements. Let's further on concentrate on linear elastic systems, and in particular linear elastic cable. That's exactly what we have in mind when we talk about cable net. We have a piece of initial length L0 where we apply some cable force S in equilibrium, a normal force, and we have a coordinate X running from 0 to L0 and distributed with longitudinal displacement U bar, which also runs from 0 to the left to the maximum to the tip on the right. If we just pull with our force S, we observe a tip displacement U, and we have this relation between the tip displacement and the distributed displacement U bar by this relation, this linear relation. And if you check it, put in X equal to 0 on the left, you receive, of course, 0, just the support as you see it here. And if you just substitute L0, you will receive the tip displacement U bar. The strain, as well known, the linear strain is simply the first derivative of U bar with respect to X, and receive this ratio as the linear strain. As we further pull here with S until we reach the intended force as head, as we want that to have in our final stage of our structure, we see these relations between the final strain, the final tip displacement, and the elongation of the bar. That quite obvious as we see. The final tip displacement U star is of course the same as the elongation of the bar, as the difference between the actual length and the initial length. We have this relation that we have to integrate epsilon star over the initial length, also called the reference length, to receive the final tip displacement. We introduce Hooke's law, linear elasticity, where we have the relation between the strain and the stress through the elastic modulus. And if you substitute everything, we just receive the relation between the strain, the actual strain, and the actual cable force through the product of E, the elastic modulus, times capital A, the cross-section of the bar in the initial state. Putting everything together, we have this relation, as you see, and if we just compare that to a linear elastic spring, we have this relation at the spring, linear elastic. We again apply a force here to the spring. Here we have the spring stiffness. Again, the spring is elongated as we pull by an actual displacement U, and you know from the spring relation that we have the relation between the force we apply, the elongation of the spring we observe, and the spring stiffness. And if you just compare these two expressions, you directly see that this ratio E times A over the initial length is nothing else as the stiffness of a linear spring. That's why we call this also the stiffness of this bar or this cable. Again, if you just extend or just further pull towards the intended force F hat, by which we would like to load our spring or our structure, straightforward, we have this relation between the applied external force F hat in the final stage and the final elongation, final displacement U star. So we can put everything together that we talk about linear elastic springs, generalized springs, if we talk about the elastic deformation of a cable, with that term to be called the stiffness of this bar or this cable. What we apply here, that is what we call theory of first order, and we can say that every system is a combination of elastic springs in the context of theory of first order. Let's do a mind experiment. We take our little spring, we attach it to the ceiling, we assume that the spring is free of mass, there's no weight, And again, we have the spring stiffness and we have initial length L0. Then we increase the force, which we apply here at the bottom, from the initial state, let's call it 0 state, to a final state, I call it here 2, where we just reach the intended load F hat. And we have intermediate state in between, where we just have increased the force, but yet not reached the final state. If you look at this intermediate state and we observe what happens, we have increased the force. Consequently, the spring became longer. And if we just measure that with respect to the initial position of this point here, we can also measure or observe the elongation of this spring. And we again apply our laws we have seen on the previous slide regarding the spring, and we observe equilibrium between the force and the displacement and the stiffness of that spring. Further increasing the load until we just reach state 2, the final state with F hat, and of course we observe now the final elongation of the spring, and we have reached the final displacement U star as on the slide before. Again, we have equilibrium. We recognize that in this mind experiment we have equilibrium throughout the complete experiment from 0 to 2. If we now apply the method of sections, just to take a look at the internal force in the spring, the cable force S, as we have called that on the previous slide, or here the internal spring force S, we observe, of course, from equilibrium that F and S have the same abs value, but have a different orientation, downward and upward, to have equilibrium. Realize that the external force F is in the same direction as the displacement U, downward, while the reactive force, the internal force S, is against the displacement U, upward, and the displacement downward. To recall the equilibrium, F and S, the values of the forces are the same, that's equilibrium. External force equal to internal force, that's how we learned it in basic mechanics courses. If we just recall our spring law, the material law, we have the relation between the spring force, the stiffness of the spring, and the displacement. So S is a function of U, a linear function. And if we substitute that above here, we can then also realize that the external force, simply because of equilibrium, also is a linear function in U. And we can also express that as F as a function of U. Again, that expresses that we have equilibrium at all times during the load increase from state 0 to state 2. We can now draw these graphs for the increase of the external force F and the internal force S, as the longitudinal displacement just increases from time 0 to time 2. And as the functions for the forces are linear functions in U, it's no surprise that we receive these straight lines, where the slope is just determined by the stiffness. And we have these relations between the actual force to the actual displacement, and the actual internal force through the spring law to the actual displacement U, as well as to the final value F hat, the intended value, and the final displacement U star, and the final internal force S equal to K times U star from our material law. The work done by the external force over the increase of displacement is simply this triangle here below this straight line, which comes from integration. If you take the integral from U equal to 0 to the actual value U, the integral over the function of the force, which is the linear function, substituting by what we have found on the previous slide, K times U, integrating over the displacement here, which has received 1/2 times K times U square, where we again recognize K times U as the value of the actual force. And we can finally write the work done as we just increase the displacement from 0 to U is simply 1/2 times the actual value of the external force as a function of u times u, the actual value of the displacement. And if we look at the internal work, that means the work done by the internal force S, we see from graphics immediately it must be the same value because these are the equivalent triangles. And if we do the integration, we receive again the same value here, 1/2 times k times u squared, the actual value of the internal force S as a function of u times u, but it is negative. And why it's negative? You see it from here, again by the section method. The internal force is in opposite direction to the external force to guarantee equilibrium. And quite obviously, the internal force is in opposite direction than this deflection displacement. And because of that, the work done by S must be negative. And as we have the same values on the left and the right side, it's also quite obvious that if we sum up the external work and the internal work, we always reach 0 throughout our complete experiment from 0 to state 2. And that's the work theorem, which applies for systems in equilibrium only. Very important. We can just animate what we did before. And as we just increase the load, you see as we just walk along the straight line for the external force F. And we see also as just the work increases as we just increase the external load. And we just receive here this value for the external work, the work of the external forces. That is equivalent the same for the internal force S. We see as the internal work is increasing. And again, we recognize the equilibrium of internal and external force for every state as we increase the deflection. And that explains the negative sign for the internal work. Let's now look at a constant initial force, S with this sub-comma. Constant means it will remain constant throughout the complete loading scenario. You see we repeat this previous slide. And we add now to this force S, which should be a variant force, this constant force S with sub-comma, which is supposed to be constant throughout loading. And you see it here in our equation that we have here this elastic term, which is increasing with u, while S with sub-comma always remains constant. You see that animated as we increase u until we reach the final state u star with the intended load as cable force S head. The S sub-comma always remains constant. The work done by the constant force can be determined again from the graph indicating the value of S sub-comma throughout the complete displacement history from 0 to the final state u star, and as the internal and the external forces also are the same for a constant force, we have the same graph for both. And if we look at the internal work, it is now the area of a rectangle below the straight line. Here's the value for the intermediate state u, and we can determine this rectangle by integration or simply by u times S sub-comma. And again, it must be negative, the internal work, simply because of equilibrium of internal and external forces. And again, the work theorem also holds. The sum of these both values here is 0 for every intermediate state. And it applies for systems in equilibrium only. And if we now look at the work done with a combination of the elastic deformation, as we just increase the elastic cable force S until we reach the intended value S head, and considering the constant initial force which remains constant throughout the complete deflection, then we can determine the internal work simply again by integrating first of all for the strain from 0 to the final strain epsilon star that holds for every point within the bar, and integrating over the complete length in the reference geometry from 0 to L0. as the internal work is a negative item, I take the negative of the negative. That means we receive finally here with minus Wi a positive value. Substituting all what we found on the previous slide, we just finally come to the final value that the negative internal work is the sum of the elastic contribution, where we just have the 1/2 because of the triangle, remember, of the final elastic value S times the final value U star, plus this S with subcomma, the constant initial force which remains to be constant, times the final displacement U star. There's no 1/2 in front, simply because S subcomma remains constant, and we have this rectangular work. And straightforward, the external work must be the negative of the internal work, just that the sum of these two is 0. Our work theorem, again, for structures in equilibrium only. Let's now look at what we call virtual work. By that we just simply mean what is the change, the variation in work, as we just apply a little change, a little variation of the strain, epsilon star. And as we have just this expression here as a function of epsilon star, we can apply the chain rule. We take the derivative of Wi with respect to epsilon star, what you see here, and post-multiply that by the variation epsilon star. Taking the integral, what you see here, and last not least, taking the integral of the strain over the x, we receive the change of the tip displacement delta U. We end up in this expression that the change, the variation of the internal work, which we call the virtual internal work, we write it here negative to receive something positive on the right hand side, is simply the sum of the intended force S hat plus the constant force S is subcomma multiplied by this variation of U star. That means a little modification of the final displacement here U star, as we just play around a little bit here with the force. Again, applying the work theorem, it holds that the virtual external work is the negative of the virtual internal work. That means the sum of these two must be 0. And that is what we call the principle of virtual work for structures in equilibrium. Important to realize is that this 1/2, what we have here in the work, is disappearing as we just look into the virtual work. A little comment about potential energy. Internal energy is stored deformation work. If we just again perform our experiment, we pull down there with the force, we have an internal work performed, and as the spring becomes longer and longer, we store energy within this spring, which you can receive just by taking away the force, and then the spring just snaps back in the initial state. The energy is stored while the spring is extended. And since the energy is stored work, it just is the negative of the work. As the internal work is a negative item, again negative, you see that the internal energy is something positive. And straightforward, the variation of the internal energy is equivalent to the negative, the internal virtual work. The external energy, instead, is the loss of potential. And if you just look at the intended force which we like to apply to our structure, you see that with respect to the initial position, which is up there we see, right, obviously we have a loss of height, let's say, which means a loss of potential of this external force F hat. And if you just determine or define the external energy with respect to the final force, the intended force F hat, you see immediately that the potential, the external potential, cannot be identical to the external work. As F hat is constant throughout the complete procedure, the external energy, the external potential, is a negative value, because it loses height. And as F hat is constant. It's a negative but linear function, negative going downward here in this graph where we just draw the energies. The internal energy is again quadratic as the word internal work, but positive. The external energy is negative but a linear function. If we take the variation of the external energy, however, we realize that it's also equivalent to the negative variation of the external work. The negative virtual external work is the same as the virtual external energy. And at the solution, at the final state where we have reached F hat and we have U star, the final deflection, we realize that it's just determined by the minimum of the total energy, which is the sum of the internal and the external energy. And we see from the graph that at the minimum we have a horizontal tangent, which means that the first derivative, or more generally the first variation, must be zero at the optimal solution, at the final solution, which states with the virtual energy as the sum of the virtual internal and the virtual external energy, it must be zero. And there you see that we have a similar or an equivalent expression for the virtual energy if we compare that to the virtual work equation. Let's repeat our mind experiment and let's now look at the potential energy. Again, we have our spring attached to the ceiling and we just perform our experiment from state 0 to state 2, which is so thought to be the state in equilibrium. Different to before is that we now apply the external intended force F hat immediately, and it's quite obvious that what we see here is not in equilibrium. The intermediate state with a little elongation of the spring by U is still not in equilibrium if we apply the external force F hat, until the final state, which is now in equilibrium as the intended force F hat now finally fits to the final deflection U star. Both of them satisfy the spring equation you see before. And if you look at the potential energy here for the internal state, the sum of the internal and the external energy, we see this elastic part here with the quadratic function of U and this 1/2. And the linear term, which must be linear simply because F hat is a constant value. You can compare it to as with subcomma from before, where we just have learned that the respective work and respective energy must be a linear term without 1/2. In the equilibrium state, and we're looking at the variation from the energy theorem, we know the sum must be 0, and we can just determine the variation of the energy from the chain law, applying the first derivative here for this expression in U and post multiply that by delta U star. And we can just rewrite it here in that term as delta U star appears twice here. And what you see here in bracket, that is exactly the equilibrium equation where the intended external force F hat fits through the material law to the final displacement U star. That's exactly what the virtual energy theorem just tells us. So in equilibrium, and that applies only for equilibrium, the internal, external virtual energies sum up to 0 and everything just fits together nicely through this variation. And the last thing I would like to comment is that in the final state where the virtual energy is 0, this is already satisfied by the equilibrium equation, what you see here in the bracket, that is 0 already, which means that the choice of the virtual displacement in the final state is really completely arbitrary. You can choose what you like here, any number. The variation of the energy is always 0. I'm almost sure that is known to many of you, and we will make use of that later, just to take the variation of the displacement completely arbitrary and concentrating on the rest, typically to the equilibrium equations. And finally, we can summarize We have learned and recalled about work and energy theorems. The deformation work was this work by the elastic forces, and the principle of virtual work we have also introduced. And recalling the layout of the workshop, we have done now the introduction and the first seminar. And we will come now next to seminar number 2 about nonlinear strains and strain measures, stress measures, and the identification of force density. Thank you.